Hello, warm welcome, everyone. Thank you for being here. Get yourself ready with a notebook for this bonus problem. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. Today we're going to finish off our summer series, welcoming the summer. Summer's tomorrow. Starts tomorrow. And as promised, we have a bonus problem. You might remember the first three of the series were implicit differentiation problems that I gave to a previous student of mine a year or two ago. But I wanted to include a little bit more fun. So here we have a bit of a doozy again. You should probably give yourself about 15 minutes. I encourage checking out the graph. It's a pretty cool looking graph. I won't give the description of the graph until the end. Don't want to spoil it. And you won't ever have to be, graphing this by hand, but I just thought it'd be a good idea to consider that at the end. So go ahead and take some time, look through these parts of the question. You can pause the video and give yourself, like I said, about 15 minutes. And if you need more, that's okay. Yeah, that's right. Part D, you're going to find the second derivative. And when you're ready, you can unpause the video, come back, and see how we did it here. Without further ado, let's get this cracking, because summer is almost here. It's not waiting for anybody. We want to find dy dx. We also want to use it to write the equation of the line tangent. You already know what I'm going to say about that, I hope. I'm not even going to look at the curve equation again. I'm going to write y minus y value equals m times x minus x value. And you'll notice they gave us the x value and the y value. They gave us a point. Or I gave you a point. That was very nice of me, very generous. So there's your x and your y value. Alright, but let's do the meat and potatoes of this. That's the derivative. So you'll notice that I threw in a nice little quotient here. You're going to have to be careful about the quotient rule. Remember how this works. Low d high minus high d low over low low, or some variation of that you might remember. However you remember it is totally fine. So we're going to take a derivative with respect to x on both sides, and fortunately the right side is pretty easy. You're not going to get a lot of fuss out of the right side. But let's carefully do the derivative of the left side. So we have low d high, which is the derivative of x plus y. That's just 1 plus dy dx. Now you notice the e to the y in the denominator here? That's kind of a red flag that we're going to be able to do something important with factoring. You'll see what I mean in just a moment. So we've done low d high minus high, that's the x plus y, d low, which is the derivative of this on the bottom. Remember that the rule for e is very easy. You just write it over again. But we have to use the chain rule. So we're going to have e to the y times dy dx. And you'll notice that e to the y comes up in both of the terms. This is all over e to the y squared, like the low squared. We will also simplify that in just a moment. The right side, meanwhile, is 0. Now, when I point out that there are two terms that both have e to the y, this is the sort of red flag that I was talking about. We're going to be able to factor out e to the y, and if you can identify this effectively, not just in an implicit differentiation problem, but in any kind of calculus problem, if you can identify and recognize e to the y is going to cause some trouble, it's going to be there for double, you can factor it out. And that's going to basically cut your work in half. It's going to make a lot of things way easier. Okay, so let's take a look at what's going to happen there. When I factor out e to the y, that's going to leave me with 1 plus dy dx minus x plus y times dy dx. And on the denominator, we have e to the y squared. Remember, that means that, or rather e to the y all squared, not just the y being squared. What we can do is multiply these exponents. So this is going to become e to the 2y. Or you could just leave it as e to the y squared. It really doesn't matter, because what we're about to do next is cancel e to the y with one of those e to the y's, which leaves just e to the y. Okay. Now we can solve this. Let's rewrite it first. 1 plus dy dx minus x dy dx minus y dy dx. See how I've distributed the negative, and I've also distributed the dy dx, because they're all getting multiplied inside to the parentheses. And this just equals 0. Now, what about the denominator? Well, this is a learning moment. This is a very important learning opportunity, actually. But for some reason, my text is not working, so I'll have to write it out. E to the y, say it with me, is always greater than 0. E to the x, e to the anything is always greater than 0. E to the y will never be 0. So I can just multiply it on both sides of the equation and sort of get rid of it, because if I multiply 0 times e to the y times anything, it's just 0. Now the last thing to do here is to isolate dy dx. So I'm going to subtract the 1, and what I'm going to be left with is dy dx times 1 minus x minus y. And I can finish this off by dividing. So that means that dy dx equals negative 1 over 1 minus x minus y. Yeah. All right, now how do we use this? We want to use this to write the equation of the tangent line at this point. And here's where you're really going to be like, bro, did you really just do that? Our dy dx at that point, which you can do this little symbol to indicate that we're evaluating it at certain values. This is going to be equals to negative 1 over 1 minus 0, which would be negative 1 over 0. What the heck? You know what happens when we're divided by 0. It's blowing up. It's going vertical. So this is actually going to be a vertical tangent line. It does not look like an E. There we go. Vertical tangent line. And what does a vertical line's equation look like? It just looks like x equals something. In this case, it's going to be x equals 1. Yeah. Okay, let's move on to part B. Part B is to find all points on the curve where the tangent line is horizontal. So what does that tell us? Well, we have to find some points, x and y, but horizontal is really important here. Horizontal tells us that the slope is 0. In other words, dy dx equals 0. So let's take dy dx and set it equal to 0. But you should identify an issue with that right away, right off the bat. Right? Do you see it? This could not possibly be 0, because in order for a fraction to be 0, the numerator would have to be 0. For example, if I were to multiply both sides by 1 minus x minus y, and also to the 0. Oops. this would say negative 1 equals 0, which is obviously not true. So our conclusion is the curve is never horizontal. And I didn't really want to ruin the surprise by mentioning the shape of the curve, but now I might as well tell you that the shape of this curve is sort of like a boomerang. If you graph it on Desmos, you'll see what I mean. It has kind of like a boomerang-like shape. I mean, I've never played with a boomerang or held a boomerang, but I've seen kind of what they look like. It has this sort of boomerang shape, which is cool. Okay, so that was like pretty easy part B, right? Because it's never horizontal. You don't really have to do any work, but I do want you to understand the fundamental setup. When you see that something is horizontal, set the derivative equal to 0. It's that simple. And since we already had an expression for the derivative, it's like super easy to do, right? All right, let L be the line y equals x plus 2. Find all points on the curve where the line tangent to the curve is parallel. Now, parallel also tells you something about the slope. It tells you that it has the same slope. And fortunately, this line is not too crazy. Y equals x plus 2. This simply has a slope of 1. Right? It's just a line with a slope of 1. So what we can do is we can set dy dx equal to 1 and solve this equation. Unlike when we had it set equal to 0, this derivative could actually be equal to 1. And we're going to do the same process that we did, which is multiply both sides by this denominator. There's also a really neat trick that I would prefer doing. You could just flip the fractions, and you get pretty much the same thing. So then you end up with negative 1 equals 1 minus x minus y. So how does this work for us? Well, let's move the x and y on the other side. And let's add 1 on both sides to get x plus y equals 2. Now, how the heck does this help us? That means that as long as x plus y equals 2, then the curve will have a slope of 1. Okay, but how does that help us on the curve if x plus y equals 2? Well, here's where the question was pretty well written, if I do say so myself. X plus y is in the numerator, so if we look at the original curve, look at the OG curve, x plus y over e to the y equals to 1, which means 2 over e to the y equals 1, which means 2 equals e to the y, therefore y equals ln of 2. Very interesting y value. And if y equals ln of 2, then x equals 2 minus ln of 2. It's like the rest of the 2, because they add up together to make 2. Right? So the point on the curve, and it is on the curve, is 2 minus ln of 2, comma ln of 2. Now that is a rather interesting result. That's the point on this original curve where the curve has a slope of 1, which means it is parallel to this line, which also has a slope of 1. And if you'd like, you can graph the tangent line at that point, and you can graph this y equals x plus 2 line, and you can see that they're parallel. Okay, we're going to finish things off with finding the second derivative. So part D wants us to find d squared y dx squared. Well, let's start off with what dy dx is. Dy dx is negative 1 over 1 minus x minus y. But I might rather express this like the following with a negative exponent, because then if I want to take the second derivative, all I have to do is use kind of like the chain rule, the power rule. So this is going to become a positive 1 when you multiply the power, and now it's to the negative 2 power. Then we just have to multiply by the derivative of the inside. So negative 1 minus dy dx. And what does a negative 2 power do? That puts things on the bottom. So we write this as negative 1 minus dy dx. And what I should have written in the question, actually sort of bad on me that I didn't do this. So if you didn't fully express this, that's okay. It was kind of my fault. I want you to express this just in terms of x and y. So this is minus 1 minus negative 1 over 1 minus x minus y over 1 minus x minus y squared. So if we work with that a little bit, it's going to be negative 1 plus 1 over 1 minus x minus y. And to make this look a little bit nicer, I mean, it's cool like that. If you're cool with it like that, that's fine. But to make this a little bit nicer, I think we should just multiply the top and bottom by 1 minus x minus y, which is equivalent to getting the same denominator, or allowing the top to be added together, basically. That's what we're doing. So we're going to have negative 1 minus x minus y plus 1 all over 1 minus x minus y cubed. And so this is just going to give us x plus y over 1 minus x minus y cubed. Very interesting there, because we started off with something that has e in it, right? Oh, and we should still have something with e in it. Oh, I guess we don't need anything with e in it. That's very interesting. That's our second derivative. So if you want to determine concavity, you would plug in x and y values, which of course have to be on the curve, into this equation, and that gives you your concavity. So I encourage you to check out the graph. It's really quite interesting. It's something kind of like that. I mean, I don't want to spoil it too much, but if you're too lazy to graph it, I want you to at least kind of appreciate the shape of it. You'll see that we have some kind of vertical tangent at some point, and we don't ever actually have a horizontal point. Even though this is getting like flatter and flatter, it never actually goes completely flat. Right. Okay, I think that's enough blab out of me. That was a nice way to wrap up the summer session. Introducing the summer. I hope you guys have a great summer and you're not working too hard. The purpose of some of these videos is just to keep you fresh with like 15 to 20 minutes of practice every day or every other day, at least 3-4 times a week, and you will be in really good shape for the AP exam. It will feel like a joke, honestly. So if you want to feel great taking calculus all year, keep watching some of these series. I'll catch you guys next time.